Physical properties are those that we can observe without changing the substance and its composition. So these would be things that could fall into two different categories. Qualitative properties, that is properties that are observational, and quantitative properties, properties that are numeric. On the qualitative side, we have things like color, odor, shape, size. On the quantitative side, we have things that are measurable: mass, volume, density, temperature. But they're all physical properties. I can observe any one of those properties, and I would be able to do so without doing any kind of actual chemistry or chemical reactions. I can observe that this wall is ugly and orange. I can observe that the periodic table over there is large and white. If I had a balance, I could observe the mass of this pen. I could do all of these things. I could observe that it's blue. I could do all of these things without doing any kind of chemical reaction. On the flip side, when we describe physical changes, they fall into this same kind of definition. Physical changes are those that we can observe without changing the substance itself. Now, most of the time when we think about physical changes, we usually think about phase changes. We already talked about all the different phase changes: liquid to solid, solid to gas, gas to liquid. But other kinds of physical changes exist as well. If I were to take this pencil and break it in half, that would constitute a physical change. I have changed some of the physical properties of this substance. It now has a different shape. It now has a different mass, assuming I've only weighed one of the pieces. It now has a different volume. But compositionally, it's the same substance that it was before. It's wood, paint, graphite, and whatever the eraser's made out of. Physical changes are of this kind. They can be observed. We can see changes in physical properties, but we see no change in their chemistry. We see no change in their composition. How do we tell that a physical change has occurred? Well, we look for a couple of telltale signs. For example, a change of state. Again, we've talked about all of these already. The 6 different phase changes that we mentioned in the last lecture would all apply here: sublimation, deposition, condensation, evaporation, melting, and freezing. We can also put among these expected changes in color. Now, what do we mean by expected changes in color? Trenton. In what sense? How would we expect that? If I'm painting, I have primary colors. I've got red, yellow, blue. If I combine the yellow with the red, what would I expect to happen? I'd expect it to turn orange. That's an expected change in color. The pigments are mixing and we get a new color. If I'm dyeing Easter eggs, I've got a white egg, I put it into the dye, it comes out blue. Well, that made sense because the dye was blue as well. If I take my favorite kind of Mountain Dew and mix it with water, it's going to turn the water the same color that the Mountain Dew was. That's an expected change. A colored substance changes a non-colored substance into a diluted version of the colored substance. Those are all expected changes in color. Those are all physical changes as a result. That's different from, let's say that I take this paper and I light it on fire. I'm going to see a color change. I might even say that's an expected color change, but it's as a result of a chemical reaction that color change occurs. If I simply heat paper in the microwave, within reason, it doesn't incinerate, it just gets warmer. Chemical changes, on the other hand, these are ones where we see a change in the chemistry, a change in the composition of the substance. In these changes, we see the conversion of one substance into other substances. Evidence of this would come in the form of bubbling, where we form some kind of a gas where gas was not before. So if I take two powders and I mix them together in water and all of a sudden they start to bubble up, that's evidence of a chemical reaction. If I see a permanent color change, like what happens when something burns, or when you have rust on your car. The metal in your car goes from a shiny, silver-ish color to a rusty brown. That's an irreversible change. You can't get that back. You can't turn the rust back into steel. Or we see a sudden change in temperature. I take two solutions, I combine them together, all of a sudden it gets really hot. I take two powders, I combine them together, all of a sudden it gets really cold. Sudden changes in temperature are telltale signs of chemical change. So let me pose this question here to the group. I have a beaker of water that is boiling on what appears to be some kind of a hot plate. Is this transformation a physical or a chemical change? Brianna? What'd you say? Okay. Brianna's saying chemical. Why chemical? Okay. Based on what we saw in the previous slide, that's not bad reasoning. The water's getting hot. The question is it suddenly getting hot? Is this a rapid evolution of temperature that is occurring? How quickly does water boil? If I put a pot of water on the stove, is it steam within seconds? No. requires a lot of energy input. The other thing that we need to look at is let's look closely at the molecules themselves here. What's the chemical formula of this water molecule here in the gas phase, in the vapor? This one's easy. It's H2O. If you look closely, you can see you've got a red ball, oxygen, you've got two white balls, hydrogens. H2O is the formula here. If I look at any one of these, I find the same exact thing. They're H2O also. So the question I'm asking myself here, do I see a change in chemical composition of the molecules in this sample of water? They were H2O before, they're H2O after. So chemically speaking, they haven't changed. This is a physical change. So to the point that you were trying to make, the key word there is sudden, instantaneous kinds of changes of heat. When you set something on fire, how quickly do you feel the heat from that fire? It's almost immediate. When you light your Bunsen burner, you can get heat off of that burner pretty much immediately. If you pop open an ice pack, it feels cold pretty much immediately. It's not a gradual thing. And that's the difference. So you're on the right track. It's just the timing is what was missing there. Adria?
What about the bubbling?
Okay. Bubbling is one of the things that we look for. However, what we also have to keep in mind is that there are certain phase changes that will produce bubbles as well. So it really does come down to the composition. So is the bubbling a result of the fact that we are heating the water? Or is the bubbling a result of the fact that some kind of reaction is occurring in the water to generate the bubbles? And the way to test that is to take away the heat. If I take away the heat and the bubbles go away, then I know that the heat was causing the bubbles to form. If I take away the heat and the bubbles are still going crazy, then I know that it was something else going on. So, think about like something like Alka-Seltzer. You take those tablets, you drop them into water, they immediately start to bubble. Why do they start to bubble? Well, inside of Alka-Seltzer, you have a solid acid and a solid base that are being held together by starch. And they're kind of kept separate from each other in the solid phase. As soon as you drop it into the water, they start to dissolve. The acid reacts with the base. And in the case of the base, which is baking soda, carbon dioxide gas is the result of that reaction between the baking soda and the citric acid that's in the tablet. You end up getting carbon dioxide gas forming. It does so whether the water is hot, cold, or somewhere in the middle. That's a chemical reaction going on. If you saw the same thing in boiling water as you did in room temperature water, that would lead you to believe that it's got to be something chemical going on instead of something physical.
I have a question.
Yeah, go ahead.
So basically, a chemical reaction that is more so when the change goes to the the element. It goes down to the element of change.
No, not necessarily. What we're looking for in a chemical change is any kind of rearrangement of the molecules. So, for example, if the water were to react with something in the air to turn into sulfuric acid, for example, that would be a chemical change. And it wouldn't involve elements at all. If I had water reacting with sulfur trioxide to make sulfuric acid, and this is what happens in the upper atmosphere to create acid rain, that would be a chemical transformation. The water and the sulfur trioxide are now completely different in their composition because they've combined together to make something new. Now, in lab this week, you saw the reaction between water getting split into hydrogen and oxygen gases using an electrolysis machine, a Hoffman apparatus. And that involved, we had to introduce some electricity, but we shock it and the water splits into its elements. That's not the only kind of chemical reaction that can exist. There are many, many kinds. And when we get into some of the later chapters, we'll get into talking about what some of those kinds of reactions are. But for right now, the way to tell a physical change from a chemical change is by looking at what was there before versus what was there after. If the two are the same, then we know it's a physical change. If they have different formulas before and after, then we know it's a chemical change of some kind. And we can get into more details of that later on in the semester. Any other questions? So now that we've established what a chemical change is, let's talk about chemical properties, because chemical properties are directly related to chemical changes. Chemical properties are descriptions of what kinds of things happen when a chemical change occurs. And these can be positive or negative kinds of interactions. So for example, we can say in the affirmative that when hydrogen and oxygen come together, they react explosively to create water vapor. Hydrogen and oxygen easily burn in each other. But helium doesn't really react with anything. That is a chemical property as well. Lack of reactivity is an important chemical property because it tells us when things are reactive and when they are not. We can talk about the rusting of iron. Chemical properties can be in terms of, well, what do we see when that happens? Well, we see something that is really strong and flexible and shiny turn into something that is brittle and weak, flakes off easily, kind of reddish brown in color, not shiny. So a lot of the things that we described as physical properties can be used to describe how a reaction occurs and what kind of reaction does occur when a chemical change is present. So we often will use physical properties to help us to describe the difference between the product of a chemical reaction and what we started with as reactant. And as I mentioned before, a lack of reactivity, as is the case for helium and the other noble gases, as is the case for gold and some of your other precious metals, that lack of reactivity is also very valuable to us as information. So now that we've talked about section 2, we're going to pivot again to numbers. And we're going to spend most of today and a good part of Monday's virtual session talking about numbers and conversions. Now, when it comes to units, we describe units as one of two ways. We have base units and we have derived units. Base units are units that have no other kind of defined quantity used for them. So there is no other way of describing distance. We can't use any other unit to describe distance to create the unit of the meter. The meter is the base unit for it. I can't combine together other units to make meters. I can't combine together other units to make kilograms for mass. I can't combine together other units to make seconds to measure time. I can't combine together other units to make Kelvin temperature. That's what it means to be a base unit. A base unit is a standalone unit. It doesn't come as a definition of other units being multiplied or divided together to get it. Derived units, on the other hand, do. Derived units are made by combining, usually through multiplication and division, other units together. So, for example, a good example of this is volume. Volume is equal to length times width times height. All three of these dimensions are dimensions of distance. And so if I take meters times meters times meters, I would get for volume the derived unit of cubic meters. And this would be the case as well for things like cubic centimeters, cubic inches, cubic feet. I'm taking a unit of distance, feet, inches, miles, whatever the case may be, and multiplying it several times over to give me the unit of cubic feet, cubic meters, liters, milliliters, etc. Now, there are other kinds of derived units, but this is the most common of them. Anytime you see a unit that involves the combination of other units, that is by definition a derived unit. So if we give you something that is grams per milliliter, which is a density unit, Well, that's a derived unit. I had to take a mass and divide it by a volume to get it. If you're measuring work in terms of newtons, you have to take kilograms and meters and seconds and combine them together in a certain way to get that unit of force. Those are all derived units. And that's what makes a unit derived or underived. Let's talk about some specific ones. Mass. By definition, mass is the measurement of how much matter is in an object. We measure mass using a balance of some kind, whether it's a triple arm balance like you might have seen in your high school or middle school days, or an electronic balance like what we have in our laboratory. Mass is measured on a balance. Now, understand that when we talk about mass, we can kind of use it as interchangeable with weight. Now, you could probably get into a great debate with a physics professor about the difference between mass and weight, but assuming that all of our measurements are being done here on planet Earth, they pretty much mean the same thing. Where mass and weight really get into fundamental differences is when the force of gravity is variable. So if I'm comparing the density of iron here on planet Earth versus the density of iron on Mars, yeah, they're going to have slightly different values because the force of gravity is going to be different there. Common unit for mass is the gram. Just to give us some context, 1 pound is approximately 454 grams. Again, just some context there to kind of help us out there. As I said before, we usually measure masses by weighing them on balances. If I were to look, a salt crystal usually has a mass of about 50 milligrams. The question here is how many milligrams are in a gram. For that, we have to have some knowledge of our metric prefixes. The prefix milli literally means 1/1000th. So each milligram is 1/1000th of a gram. That means that there are 1,000 milligrams in 1 gram. Let's use this as an opportunity to talk a little bit more about the metric prefixes. Now, certainly metric prefixes extend well beyond this table. This table is kind of the bare bones of most common metric prefixes. There are certainly others that exist. For our purposes, most of what we're going to see actually exists in this range right here. Now, that's not to say that we won't come across the occasional micrometer, or if you go to a store to buy a new phone, they might talk to you about gigahertz or megabytes of storage or those kinds of things. And when we talk about atomic size and light, the prefixes nano and pico might come up occasionally. But most of what we need to concern ourselves with is right in this sweet spot right here. In the middle here, between kilo, centine, milli, is our base unit. These values for these exponents are all relative to the base. And what I mean by that is one kilometer is equal to 10 to the third meters. 1 centimeter is equal to 10 to the negative second meters. 1 millimeter is equal to 10 to the negative third meters. When we discuss any kind of conversions involving the metric system and the base units, we can always keep these kinds of ideas in mind. Now, what's interesting is since they're all relative to that value, we can always flip them around as well. And what I mean by that is if I want to make them prefix relative, all I do is switch the numbers and change the sign of the exponent. So 10 to the negative third kilometers is equal to 1 meter. 10 to the second centimeters is equal to 1 meter. 10 to the third millimeters is equal to 1 meter. See what I did there? All I did was take the numbers here and switch them, and then turn the exponent from negative to positive or positive to negative. Why does that matter? Well, because if I had to do any kind of conversions within this system, since they're all equal to the same amount here, I can make them equal to each other. So 10 to the negative third kilometers is equal to 10 to the second centimeters. It's that good old transitive property of mathematics. If two ideas are equal to the same idea, then they're also equal to each other. All right, any questions here about the prefix system? Now, if we are going outside of the metric system, outside of the prefixes, tables of conversions like these are very helpful. Because what they do is they tell us the relationship between two values. These are not values that you need to memorize. In a situation where you had to do a conversion of this kind, I would provide you with a table like this that gives you the equivalences, and you just have to convert it properly. So let's actually leave it right there for today, and we'll call it a weekend here. So on Monday in Zoom, we will talk more about unit conversions and calculations. That's the last big hurdle that we have to climb before the end of the chapter. Friday next week, we'll probably get into a little bit more in terms of talking about energy and just some base definitions, kind of closing out the chapter as a whole. And that's when that section 3 and 4 post-lecture will come up as well. But for this weekend, post-lecture 1.2 is due Sunday night in Connect. So don't forget about that assignment. Once the portal closes, it doesn't reopen. So make sure that you take care of that sometime this weekend. Have a good weekend. I'll see you virtually on Monday.